previous lecture. Now, on our previous lecture, we discussed the general picture again. And one of you, when we were chatting, they were saying that we were repeating the same. He feels like we are repeating the same thing over and over again. And in fact, yes, we are repeating the same thing over and over again. We will keep repeating the same thing over and over again throughout the semester, in fact. And one of the points that I will keep on emphasizing is that what we do here is not that much different from what you will be doing in quantum mechanics, or what you had already done in quantum mechanics. So in that sense also, this course, to a large extent, is a repetition of your quantum mechanics, with some of the techniques, but just with a different terminology. And then we looked at the symmetries. We said, okay, we had already discussed the Noether theorem, and then we looked at some of the conserved currents that we could drive. We had looked at the we had calculated the U1 charge, which could also be identified with the electric charge if there were electromagnetic interactions in this theory. That is also something we will look. And then we looked at SU2, in general SUN theories. There are more than one charges in those theories because the symmetry is larger, and hence there are more charges. And that was where we had left. So are there any questions, anything you want me to repeat before following with the lecture? Now today, there are basically two things I would like to discuss. One is the energy momentum tensor. Okay, this is just another application of Noether theorem. I mean, in our first lecture, the symmetries we talked about were symmetries that change the definitions of the fields or that mix the fields among themselves. So those symmetries are what we called internal symmetries. Now, we had also talked about the Lorentz symmetry, the Poincare symmetry. For example, the Poincare symmetry contains translations. And the Lorentz symmetry, and both of them, in fact, contain rotations and boosts. And these symmetries are what we call, because here in this case, in these symmetries, we are changing the space. These are called space-time symmetries. And well, translation symmetry in space and time will give us the energy momentum tensor. Rotational symmetry and boosts will give us the angular momentum tensor. And then after this energy momentum tensor, I would like to discuss, we will start the perturbation theory. What Schwartz calls the old-fashioned perturbation theory. And my main aim there will be, I mean, you have probably heard, at least those who have had some experience with Feynman diagrams, you have probably heard of the terminology, the virtual particles, a particle being off shell. So we will see what they are. Now, first, let's start with the energy momentum tensor. Well, let's start with translation symmetry. Well, basically, things shouldn't change if you just translate your reference coordinate axis. But that means that, let's say that in one coordinate axis, if your coordinates are x mu, in some other coordinate axis, your coordinates will be x mu plus a mu. How do functions change? So if you have a function of x mu, this will become the function of x mu plus a mu. If a mu is small, well, that's usually what we do in Noether's theorem to identify the charges. We look at infinitesimal symmetry transformations. Then this will be f of x mu plus a mu. Well, let me use a different symbol. A nu del nu f of x mu. So the variation in our function due to this symmetry, let's say delta x mu, x nu, will be del nu f of x nu. So remember, in our Noether theorem, we had to calculate the derivative of the Lagrangian and multiply it with the variation of the fields itself. Now let's look at the Lagrangian. Lagrangian itself, being a function of the fields, well, it's actually a function of the coordinates. Well, not directly, but it can have explicit dependence, but if it has explicit dependence, then we don't have translation symmetry. But Lagrangian still depends on the coordinates through the fields themselves. So if you make a translation, the Lagrangian will change, but it will take a total derivative. You see, when we were using the Noether theorem, we said that the Lagrangian should be invariant, or the change in the Lagrangian should be a total derivative or for divergence, for gradient. Well, in this case, that is actually the case. But if you look at the left-hand side, the dependence of the Lagrangian on x nu are through the fields. So I can write that as derivative of the Lagrangian with respect to phi times the variation of phi. Well, you can imagine we can cases where we have more than one fields, plus derivative of the Lagrangian with respect to the derivative of phi times the variation of the derivative of this field. This should be equal to x nu. Well, let me divide by del x nu. So this equation should be satisfied. Now we will do the same trick. The second term, I can write it as, let's say, minus del nu, the derivative of the Lagrangian with respect to the derivative of the field times the variation of the field with respect to x alpha, the shift. Let me also move the del alpha to the left. This should be equal to 0. Well, this term and this term, they will cancel each other thanks to the equation of motion. So I can just cancel them. And I am left with del nu derivative of the Lagrangian with respect to del nu phi, change in the field per translation, minus G alpha nu L. This should be equal to 0. Well, if you multiply del nu with G alpha nu, you get the derivative with respect to X alpha. And what is del phi by del X alpha? Well, just go back here. Phi is just some function that depends on the coordinates. That is derivative of the phi field with respect to X alpha. So we have del nu derivative with respect to the derivative of the field times the derivative of the field with a different index minus G alpha nu L. This should be equal to 0. So here we have a new conserved curve. But note that it has two indices, alpha and nu. It's not just a single vector, it's a tensor. T nu alpha. And for each alpha, we have 4 of them, it is something conserved. This is called the energy momentum tensor. Well, the conserved quantity, corresponding conserved charge is just take the 0 component, integrate over all space. This is the conserved charge. Well, in particular, let's look at P0. This is the integral of T00. Well, T00, if you look at this expression, note that this derivative is nothing but the momentum, conjugate momentum to the field phi. This is pi nu. So this is equal to pi 0 times phi dot minus the Lagrangian. It's pi q dot minus the Lagrangian. This is nothing but the Hamiltonian of the system. And for the other components, you can just calculate. For other components, you will see that it's actually the momentum. So you will see that in particular P. Okay, I'm just kind of lazy writing out these exercises as a PDF and upload it in OptoClass. These are your exercises that I would advise you to do. I'm not writing these down as a nice LaTeX PDF document and uploading them in OptoClass, but these are the exercises I would advise you to do, in addition to the ones that are already in the book. So if you calculate the other components, you will see that the space components will just give you sum or integral over all momenta of k, ak dagger, ak for the real scalar or the complex scalar. For the real scalar field, this will be the momentum, plus maybe some constant. Now, you see that ak dagger ak just counts the number of particles you have, how many particles you have having the momentum k. If you multiply it with the momentum they have, this gives you the total momentum. So any questions here? Well, this is just the translations. In Lorentz symmetry, we have the rotations and the boosts. Well, the first thing you have to figure out, look up in some books, how can you represent what are the operations of Lorentz symmetry? How does the four vector change in general? Well, we had already seen that x mu will become lambda mu nu, x nu under a Lorentz symmetry. If you look for an infinitesimal transformation, this lambda mu nu would be Kronecker delta mu nu plus, let's say, omega mu nu. What are the possible omega mu nu's? How can, in terms of which other tensors you can express this omega mu nu? Because if mu nu is just I and j space components, it will be rotations. If it contains the zero component also, it will be boosts. Have a look. Now let's go back to the energy momentum tensor. This is what we define. For example, let's just look at the real scalar field. This is a possible Lagrangian that we have been playing around with. Well, the corresponding energy momentum tensor would be the derivative with respect to the derivative of the field. We'll just give you the derivative of the field. It only gets contribution from this one. Del nu phi times del alpha phi. Then we have minus g alpha nu times the Lagrangian itself. Okay, one thing I want you to see in this Lagrangian, in this energy momentum tensor, is that T nu alpha is actually equal to T alpha nu. It's a symmetric energy momentum tensor. But if you look at this definition, okay, the last term is symmetric under the exchange of indices, but there is no reason for the first term to be symmetric under the exchange of indices. It's just for this case, for the real scalar field, it turns out to be symmetric. And some of you were mentioning that these conserved charges are not necessarily unique last week or the last hour, because you see, as long as, well, they are not unique, basically the Lagrangian is not unique. You see, for a given system, if you have this Lagrangian, which you can use to obtain the equation of motion, this Lagrangian is also valid. So you can have different Lagrangians for a given system. So if you have different Lagrangians for a given system, in general, although the equations of motion will be the same, well, these will not. The conserved charges might be different. And it turns out that, in fact, you can always come up with a definition of the energy momentum tensor that is symmetric. Okay, quite a number of you are already working on GR. You see, the metric couples to the energy momentum tensor. The metric is symmetric. So the energy momentum tensor that you can derive from the derivative of the Lagrangian with respect to G mu nu, this will be symmetric. This will be the symmetric energy momentum tensor. Well, the difference between this symmetric one and this here, the anti-symmetric one, you see, if you note our currents that we derive, they are conserved only if the equation of motion is satisfied. Without equation of motion, they will not be satisfied. But there are currents you can come up with that will be always satisfied, independent of your equations of motion. So if you add such a current to your conserved current, you obtain another conserved current. So the difference between these two energy momentum tensors is basically such a term that is always, divergence of which is always zero.
When we take the derivative of kinetic term, it has Lorentz contraction, so if the metric is vara in place, then the derivative should act on to the metric also.
The derivative should
act on metric in the kinetic term.
Yeah. Now you see, in GR, the metric doesn't only appear over here, it also appears in your d4x integral. d4x, there's also the metric over there. So you have to also take the derivative over there. With that correction, this gives you the symmetric energy momentum tensor. If you don't know GR, if you haven't taken GR, you can just forget about this. Just note that you can still define a symmetric one. And in fact, this solution will give you a hint. Look at the end of the chapter in Schwartz, where this is from the end of the chapter questions. There it also tells you how to obtain the symmetric energy momentum tensor without using GR. Okay, any questions up to here? So whenever you have a symmetry, it means the Lagrangian should be either invariant under that transformation or should differ at most by a total derivative. Then Noether tells us that there's a conserved quantity, and all the conserved things we know are actually because of these symmetries. So if you have translational symmetry, energy and momentum is conserved. Translation in space and time corresponds to the conservation of energy and momentum. And in fact, last lecture, we had also seen a case where, for example, we defined the charge, and the commutator of the charge with the field itself gave us how the field is transformed. So if you have a charge, you also know how the fields should be transformed. So it's a if you have a conserved thing, you have a symmetry. If you have a symmetry, you have a conserved thing.
In GR, we should take absolute volumetric.
Well, it depends on how you define the metric itself. In my case, that is minus G, minus the determinant of G is negative, minus G is positive. So I don't need absolute value. So let's start with perturbation theory. In Schwartz, it's called the old-fashioned perturbation theory. So what would we like to solve? Well, we had looked at this theory, in fact. We had identified the spectrum, the energy, we had the annihilation creation operators, so we can just create many different states using these annihilation and creation operators, and we also identified their energies. So in a sense, we solved this Lagrange, the system described by this Lagrangian. No, this Lagrangian, without the V. When we put the V, in general, we don't have a solution. We don't have an exact solution. That is where we need to know approximate solutions. So we will have a theory. And furthermore, just keep in mind that I will be dealing with Lagrangians. But if I have a Lagrangian, I can write the Hamiltonian. The Hamiltonian of my system, did I write? I should have written it somewhere. Okay. If you just take the zero component, not the space components, but the time components, the k will be replaced by omega k. That is my Hamiltonian. If you have additional potential terms over here in your Lagrangian, If you have additional potential terms, well, you can also expand the fields in your potential terms in terms of the annihilation creation operators, and you will get additional terms with more than two operators multiplied with each other. Then we cannot solve it. That's the part which makes our problem difficult to deal with. But that will be the Hamiltonian. I can always work with that Hamiltonian also. I don't need to know the Lagrangian. I can have my Hamiltonian, write down my states, whatever those states are. I can always expand those states in terms of the eigenstates of H0, which will be states with no particle, one particle, two particle, three particles, etc. And I would be interested in finding these solutions, if not exactly, approximately. So let's assume, not really an assumption, we solve H0. And we would like to find the solution of this H is H0 plus V. Well, this separation is also kind of arbitrary. As long as you can solve for H0, you are good to go. At this level, it's arbitrary. So you just separate your Hamiltonian into a part that you can solve, into a part that you cannot solve. And I would like to find a solution of this equation. Now, I will be interested in particles moving around. So they can, in principle, have any energy. The energy levels will be continuous. So I might still look for solutions that have the same energy. Well, what I can do is this will be H0 plus V. Psi is equal to E times psi. Or H0 minus E. Psi is equal to V times psi. The left-hand side is something I can solve. The right-hand side just complicates my problem. Well, the formal solution of this equation will be this is a formal solution. Well, this is the particular solution. Particular in the sense that for the inhomogeneous equation, this is the solution of the homogeneous equation. Well, how did I choose the homogeneous equation? Well, I assumed that I imposed an initial condition or boundary condition saying that if V is equal to 0, my solution should reduce to this wave function, this solution. So that's why I have the phi over there. Well, this is not very helpful, to be honest. It's a formal solution. Well, there are a couple of problems with this expression. One is here, 1 over H0 minus E, or H0 minus E inverse. I'm assuming that this operator has an inverse, which it does not, because it has a 0 eigenvalue. Since if you have an operator with a 0 eigenvalue, you cannot invert it. That's not a problem. Again, for those who haven't taken quantum mechanics 1 or 2, you see the solution is just add an I epsilon over here. So it becomes a invertible operator, and you are fine working with it. Why does it work? Again, quantum 507 or 508. So that I will leave to your quantum mechanics courses. Still not exactly a solution because I'm trying to find psi. Psi appears on the right-hand side, but I can iterate it. So if I have psi, this is equal to phi plus 1 over H0 minus E. I will not write the plus I epsilon. Just keep in mind that although it's pathological, this expression, there are ways of avoiding the problem times V. Well, now I have a psi state over here, but the psi state I can use this equality to write that psi state. So I would get V phi plus 1 over H0 minus E V 1 over H0 minus E V psi. Well, I can repeat the same procedure over and over again. So, for example, I can replace
E0 or
H0. I can repeat this procedure over and over again, and I can obtain a longer and a longer expression. The thing you should note over here is, you see, this term doesn't contain any V. It's V to the power 0, if you like. This term is of the order of V. This term is of the order of V squared. Well, if you write more and more terms in this expansion, all the higher terms will be of the order of V cubed, V to the 4, V to the 5th, etc. So if, in some sense, V is sufficiently small, you see, V is an operator. It doesn't make too much sense to say that V is small. But if you can somehow, for a particular problem, make sense out of this expression that V is small, so that you can ignore the higher order terms, so you get an approximate solution. Well, usually what is also done is, rather than working with these states, let's go back to this expression over here. Now, the problem over here was I have a solution for psi which involves psi itself. So I would rather write the solution of psi in terms of phi only. Well, that means I have to somehow write V of psi, that is the part that contains psi, in terms of phi. I'm now just inventing some operator that, when acts on phi, would give me V of psi. What is this T? I don't know at the moment. That is something I invent. But V of psi is some state in my Hilbert space. Phi is some state in my Hilbert space. And in principle, I can just rotate one to the other one in my Hilbert space. So that T is what does this rotating T of phi into, what rotates phi into V of psi. So if I do this, then I have this equation. Well, still not much helpful. You see, okay, the right-hand side doesn't depend on psi anymore, but I don't know what the hell this T is. So let me multiply both sides by V. Now, why did I do that? Well, on the left-hand side now I have V of psi, which is nothing but T of phi. So this equation has to be satisfied whatever phi is. I mean, you can choose different initial states. You can look at different, you can start with different eigenstates of the so-called unperturbed Hamiltonian. So for this equation to be satisfied for all phi, the operators multiplying phi should be equal on both sides. This is called the Lippmann-Schwinger equation. Well, it's actually just another way of expressing basically this equation over here, or this one. They are the same equations. In one case, I'm looking for particular states. Here, I have a general operator equation. If you like, that's the only advantage of this. Well, I can do the iteration procedure on this operator. So T will be V plus V 1 over H0 minus E. Well, instead of T, I can just substitute the whole expression, which will give me v plus v 1 over h0 minus e v. Now I can 1 over h0 minus e times t, but instead of t, again, I can substitute the whole expression, v plus, well, you see the pattern, you see how it will go to infinity. And in general, what we will be interested in is these matrix elements. So how can an initial state, let's say I have an initial state I, evolve into my final state F? For example, this is what we will be calculating when you have electron scattering. Initially, you have two electrons with some momentum, and then finally, you see two electrons with different momentum. What is the amplitude for this transition? That will be determined by this T over here. So this will be our object of interest. How can we calculate these transition amplitudes? In quantum mechanics, you will see again at the end of 507 or at the beginning of 508. But how will we calculate them in field theory?
I didn't understand from 508 either. Why does this give me the amplitude?
It gives, you see, what is T of I?
Right. Go up, I'll see the expression is here. T of I is V of phi, right?
V of psi, right? Okay. Let's say psi I. Now, what we would like to calculate is psi I times the final state, right? What is psi I? It is this one. Final state, initial state. Let me in fact use this one. No, this one over here. There is plus 1 over E final minus E initial FTI. I'm using this expression over here. No, not this one, this one. So you see, if I know this quantity, I will be looking at when my initial and final states are different. So this will be 0. They will have different momentum, for example. That will be 0 in the cases I'm interested in. And if you see that F psi I is actually proportional to FTI. Okay, that is why I'm interested in this matrix element.
What if the energies are the same?
There's all this machinery of I epsilon, the reduction formulas, etc., which gets rid of that factor. When we are calculating quantities of interest, like the cross sections, we will study the cross sections, scattering cross sections. This term doesn't appear. Cross section depends on this matrix element only. So this is what I'm actually interested in.
Why do I call it amplitude, Tom? Why do I call it amplitude?
What is your proposal? What should we call that?
Something.
T is called the transition matrix.
Yeah.
It describes the transition from an initial state to a final state. And amplitude is everything we call, which, okay, you can say that it's the matrix element of T, but Ti is basically the final state. So here we are just looking at the overlap of the final state with, the time evolved state with the final state I'm measuring. And those matrix elements between two states, we always call them amplitudes. That's why this is an amplitude. This is the transition amplitude. But if you want, you can also give it the name alluvial wave element, but nobody will understand that soon.
I'll write something.
Okay. Any other questions? Now, what is this FTI? FTI. Well, let's go back. This is my T. over here. This will be equal to final V initial, just the matrix element of the interaction potential, plus FV n, no, let me write it, FV 1 over H0 minus EV I, plus the other terms. Well, I can insert an identity over here, sum over all n. I'm writing a summation, but they can also be an integration if the eigenstates are continuous. This will be FVI plus sum over n FVN 1 over En minus E, let me put EI, and VI. Or if I use the matrix element notation, TFI will be equal to VFI plus sum over n VFN 1 over En minus EI VNI, plus, of course, all the other terms. Well, why did I put all n is not equal to I? Well, if n is equal to I, that term basically diverges, but you can actually prove formally that n is equal to I term doesn't appear in that sum. It's usually the way to avoid the singularity of this. The inverse operator of H minus E is, in the case of discrete states, while the degenerate states do not appear in that sum, you can make sure that the degenerate states do not appear in that sum, so you don't have the divergence problem. If you have a continuum of states, this plus I epsilon prescription, you can actually prove it that is the correct prescription, and then you don't have any divergence problem. So what does this tell me? How can I interpret this? Well, if I'm looking for the transition of my I state into some final state, well, this expansion tells me that it is possible that I state makes a transition directly to the final state due to this action of V, or my I state makes a transition to the nth state, and then that nth state makes a transition to the final state. And at each of these vertices, now let me put the arrows. Well, at each vertex, I have the matrix element of V between the outgoing state and the ingoing state. Also here, V and I, V, F, N. And if there is such a line connecting two interaction vertices, those are so-called, these crosses are interaction points with the external potential, I have this 1 over En minus Ei. This is called the propagator. What is En? En is the energy of the state that is propagating between those two interaction vertices, if you like this analogy. Ei is the energy that you send. Well, you will quite often hear that energy is not conserved. You send a particle with energy En in a state Ei, then it evolves into a state, at least for some time, to a state with energy En. If En and Ei have to be different, otherwise this expansion doesn't make any sense. And if En and Ei are different, then, well, there's no energy conservation. But just keep in mind that E is an energy. You see, these I states are not energy eigenstates of my Hamiltonian anyway. You see, I have a Hamiltonian H. H of E is not equal to Ei of E. H0 of I is EI of I. But my system is described by H, not H0. So I state is not actually an eigenstate of my Hamiltonian. So saying that EI is not conserved, well, so what? It's not an energy eigenstate anyway. I can expand that I state in terms of energy eigenstates, and each one of those energy eigenstates will have energy different than EI.
I don't understand.
So, I mean, energy conservation is valid even in this case, but you have to be careful about what you mean by energy conservation. I create a particle at a large distance. At a large distance, there's no potential. So EI is an energy eigenstate. If I would like to measure the energy over here, I have to interact with my system. If I interact with my system, well, I will also deposit some energy or take away energy from my system. You also have to take into account all of those effects. And at the end of the day, energy will be conserved, even in this system. But we will still talk about saying that energy is not conserved because of the energy-time uncertainty relation. For short intervals of time, energy need not be conserved. So that we will still stick with that description of this process. But at the end of the day, EI state and EF state, the initial and final states, if they are asymptotic states, they should have the same energy eventually. So any questions up to here? Yes?
How can we write, after you insert resolution of identity, how do you write EM?
Well, you see, I have this one. After resolution of identity, you see here, I get FVN and 1 over H0 minus EVI. Now, EI is actually what I call E in the previous steps. But here, H0 operator, when I act on this ket N is an energy eigenstate of H0. This is just FVN 1 over En minus E and VI. Now, in the next hour, okay, so this is our scattering process. We are interested in calculating these matrix elements. Let's do an application to, suppose I have a phi1 particle with momentum k1. This is my initial state. And I have let's say, the same kind of particle with momentum k2. My final state will be phi1 kind of particle with momentum p1 and another phi1 particle with momentum phi2. Their momentum should change. And V, I will take V as, let's say that they're all real fields, phi1 of p1, phi1 of x, phi2 of x, phi1 of x, with some coefficient over here, lambda. Phi1 and phi1 are one kind of a real field, phi2 is some other kind of a real field. And we will see if such a potential will lead to a transition from I to F and what will be the transition amplitude. Okay, so let's give a 10-minute break, and then we will continue after the break.
Can I show you some